All right, so I'm going to go over question 20 from the practice final that I handed out on Friday. And as you can see here, we're dealing with a typical three-wire circuit. So as you know, a three-wire circuit is going to consist of a line 1, a neutral, and a line 2. Split between the neutral and line 1, you're going to have 120 volts, and line 2 you're going to have and neutral negative 120 volts. And between line 1 and line 2 you're going to have 240 volts. And this is the system that we use in all residential housing so that we have access to two different voltages, and we can also, it's also safer. We got a grounded neutral, and the benefits are huge. So in this particular question, we're given the resistances up here of the conductors themselves. So every conductor has an internal resistance that we need to account for, and that internal resistance is going to create a voltage drop along the conductors, which is going to eat into the voltage available at the loads here. So though we have 120 volts at the source going to the load 1 here, we're not going to have 120 volts available at load 1. Some of it is going to drop, and that is called line drop or voltage drop. Likewise between neutral and line 2. So the first part of the question here is we need to be able to calculate the voltages at load 1 and load 2. So the first thing we got to do, or the first thing I would do, is to redraw the circuit and adding the values that we know. So along this resistor here, R1, we got a resistance in that conductor equivalent to 0.1 ohms. Then we have our load. We got load 2 here. Now we don't know what our resistance is on those loads, but what we do know is the current flowing through. So we got 3 amps going through line 1, or load 1, sorry, and we got 14 amps going through line 2, or load 2. Then we have a neutral here. Oh, before I get too carried away, we got a resistive value made up of the internal resistance of the neutral conductor, and that has a resistance of 0.2 ohms. And likewise here, we got an internal resistance of 0.1 ohms along line 2. So that's the information we're given. The rest of it we need to, and we know, that we got 120 volt source, 120 volt. Yeah, we get the 120 volts as well. Okay, first thing I want you to recognize here, I'm going to just change my pen, is that we have a very unbalanced three-wire system here. We got 3 amps flowing through load 1 and 14 amps flowing through load 2. And in a typical three-wire circuit, we want to make sure that the loads are as balanced as possible. In this case, it's not. And there's going to be consequences if the neutral breaks, and we're going to tackle that part of the question in part 2 of question 20. Either way, we got to start trying to calculate information that we do indeed know. So the first thing I want you to recognize is if we have 3 amps flowing through the load, we can give that a direction. Now in 120, 240 volt AC system, the direction of the current is going to change change back and forth 60 times a second. So it doesn't really matter what direction we give it as long as we stay consistent. So if we say the direction is flowing this way during the instantaneous snapshot we take of the circuit, then it must be flowing this way, and counterclockwise or clockwise around the entire circuit. Now, in 1/20th of a or 120th of a second, it's going to flip back and go the other direction, but it doesn't really matter. It's not going to change our calculations in the slightest. So if we have 3 amps at load 1 here, that's going to mean that because this is a single conductor, this resistor is in series with the load, we must have 3 amps going through that conductor. And if we have 14 amps flowing this way through load 2, we must have 14 amps flowing through this conductor here. Now, as we know, if we have 3 amps going this way, and all of a sudden we have 14 amps on this load, well, that 11 amps difference needs to come from somewhere. And that's what the neutral does. It deals with the imbalance of the 3-wire system. So the 11 amps is going to flow up through the neutral. The 11 amps is then going to converge with the 3 amps coming down load 1 to create the 14 amps we see on load 2. So we have 11 amps going up in this case. All right. Now, with that done, we can calculate the voltage drops that occur in the conductor, or the line drops. So we got 3 amps, and to figure out the voltage drop, we just use Ohm's law. So V equals I times R. 3 amps times 0.1 ohms is going to give us 0.3 volt drop along that conductor. If we got 11 amps going through the neutral and a 0.2 ohm internal resistance, then we're going to have 2.2 volt drop along that conductor. And here on line 2, 14 times 0.1 is going to give us 1.4 volt drop along that conductor. Okay, so these drops are going to affect the voltage we see along our loads. Now, to figure out our voltage drop on our load, we need to remember Kirchhoff's voltage law, which states that the voltage rise plus the voltage drops need to equal 0. So we got to do something called a little loop calculation here. So we're going to draw in a loop, and our loop needs to go in the same direction as the current going through line 1. So we're going to maintain that clockwise loop as we calculate our voltage drops from line 1 to the neutral, as well as the neutral to line 2. So we start off with a voltage rise of 120 volts. So we start out with plus 120 volts. Now we got a voltage drop along this conductor of minus 0.3 volts. Now we don't know what the voltage drop is on load 1, but we do know that we're actually going to have a voltage rise of 2.2 volts along the neutral. Now, why is it a rise in this case? Well, it's because our direction of our loop and the current going through our neutral are opposing each other. And that opposition is going to create a voltage rise rather than a drop. All right, so we got plus 2. So if we take our 120, subtract 0.3, and add 2.2, we end up with 180 121.9 volts. That 121.9 volts is the voltage drop that we would need to see on load 1 to make these numbers equate to 0. So all we do is we're taking our voltage rise, our source, 120 volts, subtracting our first voltage drop. We recognize that the 2.2 volts in the neutral is going to be a rise. And if we calculate that, it's going to come out to 121.9. So that must be the voltage drop that we see at load 1. Okay. Let's do the second half of the question. So between neutral and line 2. And this time I want you to recognize that the voltage drop on our neutral here, it's actually going to be a drop. So we start it with 120 volts and we subtract 2.2 volts this time. And that is because the current flow through the neutral is traveling the same direction as our loop. If that occurs, and this is only going to happen in the neutral, if that occurs, it's now going to be a rise. And another way of looking at it is if it were a rise on this side of the equation, then it must be a drop on this side of the equation. All right, so we end up with we got 120 volt source, subtract 2.2 volts, as well as we subtract the 1.4 volts. So any voltage drops in the lines themselves, this one and this one, they're always going to be a drop. It's only the neutral that sometimes becomes a rise. Okay? So if we add that up, 120, or calculate that, 120 minus 2.2 minus 1.4, it's going to give us 116.4 volts. And the reason these voltages are so different, 121.9 volts and 116.4, is again because this circuit here is very imbalanced. So the answer is going to be load 1 has 121.9 volts, load 2 has 116.4. It's going to be B. All right. So let's do the second part of the question here. If the neutral was broken, the line current would be what? Well, again, in a completely balanced circuit, there's actually no current on the neutral. And that's, again, why we want to balance our three-wire systems. If it is very unbalanced, like the question here, there's going to be a lot of current on the neutral, in this case 11 amps. And if the neutral were to open, all of a sudden the voltages along our load are going to be very, very different than the 120 volts that they ought to see. If it was balanced and the neutral were to open, then you would still maintain that 120 volts or ish 120 volts along your load 1 and load 2. So what we got to do to calculate with the neutral broken is we need to figure out what the resistances are going to be on load 1 and load 2. And that's no problem. We can do that because we know that this is 121.9 volts with the current of 3 amps. This one's going to be 116.4 volts with a current of 14 amps. And because we know the voltage and the current, we can figure out, using Ohm's law, what the resistance is. So R equals V over I equals 121.9 over 3. In this case, it's going to be 116.4 over 14. That's going to equal 121.9 divided by 3. So this is going to be 40.6 ohms, which makes sense. It's got a high resistance, so it's limiting our current to 3 amps. And load 2 is going to be 116.4 divided by 14. And this is going to be made up of a very low resistance relative to load 1, which makes sense because our current is quite high. Okay, so it's important to recognize that the resistive values of the loads are never going to change, right? If you think about like a motor, it's got a set resistance. It's not going to change. It's dependent on the resistance of the copper windings inside that motor. So these are set values. What does change is our voltage drops along those, as well as our current. So we can get rid of those numbers here. Without the neutral now, that's going to be very different. So let's cross out our neutral. It no longer exists. And because we don't have a neutral anymore, we don't have that 120 volt option anymore. Between this point and this point, we got 240 volts. That's it. And now what we're looking at here is we got 4 resistors essentially in series with one another. Now we know the resistive values of the conductors. That was 0.1 ohms and 0.1 ohms. The neutral doesn't matter anymore. It's open, so there's no current flowing on it. So we have 4 resistors in series with 240 volts. Okay. So in this case, we know what V total is. It's equal to 240 without that neutral. Our resistance total, what do we do in a series circuit to figure out the total resistance? In series, R total is equal to R1 plus R2 plus R3, etc. All we got to do is add them up, right? So 0.1 plus 0.1 plus 40.6 plus 8.31 gives us a total resistance of 49.1 ohms. Okay. Now let's go up. If the neutral was broken, the line current would be. So what is the line current in a series circuit? Well, the line current is going to be the total current, because we only got one path for the current to travel along. And remember that in a series circuit, I total is equal to the current going through resistor 1 equal to the current going through resistor 2, resistor 3, etc. Everything's going to be equal. Current's going to be the same throughout the circuit. So our line current is equal to current total, and we can figure that out. I total is equal to V total over R total. Now sometimes you're going to see E instead of V for electromotive force. Alright, so in that case we got 240 volts divided by total resistance, 49.1, is 4.89 amps. Okay, so let's see if that's an option. Up top here, we got 4.884. That's the closest one. So B is our answer. Now, why didn't I get 4.884? It's because I rounded. I got a little bit of a rounding error, but as you can see with multiple choice, it's not a huge deal. We just take the closest answer. And that is how we do question 20. Quite a bit to it.